In example 2, the piecewise defined function we are going to look at is g of x is equal to x plus 3 if x is less than negative 2, and negative 2x minus 3 if x is greater than or equal to negative 2. All right, so we're going to do the same four things with this particular piecewise defined function. We're going to graph it, then we're going to evaluate it, then we're going to find the domain and range, and lastly, we will discuss its continuity. Okay, notice that this piecewise defined function also has two rules. Okay, so here is the first rule, and then here is the second rule. Okay, we are going to make a table of values to graph each piece out. The first thing to do, though, is recognize where the rule changes. Okay, so look at your if conditions. Okay, one rule is going to exist if your x values are less than negative 2, and the other rule exists if your x values are greater than or equal to negative 2. Okay, so here the rule changes at x equals negative 2. Okay, so I am going to put a vertical line that's dotted, okay, at x equals negative 2. Okay, so through here, okay, like this. Okay, this is not part of the graph. This is simply a reminder, okay, that we're going to have a piece of one graph to the left of this vertical line, and then we're going to have a different graph to the right of this vertical line. Okay, the rules cannot cross. Okay, meaning if you graph one piece, it cannot cross the green vertical line. Otherwise, you will violate the vertical line test. Okay, this must be a function when you graph it out. Okay, we are going to start with rule 1. Okay, so I'm going to come to the left here, and I'm going to write down rule 1. We're going to make a table of values. Okay, so here we go. Let me set it up. Okay, we will again be in charge of x. And then we will plug each x value in to get a corresponding y value. Okay, so here we go. We're going to pick our x values. We're going to plug into rule 1. Rule 1 is x plus 3. Okay. All right, so we've got to pick our x values. Again, you cannot pick anything you want. You have to start, the very first thing that needs to go in your table is the x value where the rule changes. Okay, so the rule changes at x equals negative 2. Okay, so then we have to look at the if condition for rule 1. Okay, for rule 1, this rule applies if the x values are less than negative 2. Okay, so we can pick things like negative 3, negative 4, negative 5, and so on. Okay, so we're going to take each of these x values, plug into the formula to get the corresponding y value, and then that will give us a point to plot. Okay, so if x is negative 2, the y value is going to be negative 2 plus 3, which is 1. Okay, so the corresponding point here will be negative 2, 1. And then we'll move on to x equals negative 3. Okay, so the y value will be negative 3 plus 3, which is 0. So if x is negative 3, y is 0. If x is negative 4, the y value is going to be negative 4 plus 3, which is negative 1. So if x is negative 4, y is negative 1. And then lastly here, and you can do more. The more you do, the better it looks, but you don't want to do too many. You'll be here forever. If x is negative 5, you'll get y is negative 5 plus 3. That's negative 2. So that's the point negative 5, negative 2. Okay. Before you can plot these points, you need to check where the rule changes. Okay. The rule changes at negative 2. You have to check if this is an open circle or a closed circle. Okay, so remember what you have to do. Okay, was it actually legal to plug in x equals negative 2 into this rule x plus 3? Okay, well, if you look at the condition, it only holds if your x values are strictly less than negative 2. Okay, it doesn't hold if you don't have less than or equal to here. Okay, it's strictly less than. So you actually cannot plug in negative 2 to this rule. It's not legal. That tells you this point, negative 2, 1, is going to be an open circle. We have to exclude that point because we really weren't allowed to plug in negative 2 to this function. Okay, everything else will be closed. Remember, what have I told you 1,000 times already? The only place you can possibly have an open circle is where the rule changes, so along that green dotted vertical line. Okay? All right, so here we go. We're going to go ahead and plot out these points. Okay, I've got an open circle at -2, 1, and then I've got a closed circle at -3, 0, a closed circle at -4, -1, and then a closed circle at -5, -2. Okay, so you can see the graph starting to come together. Okay, the points are falling along a line, which makes sense. If you look at your formula, you have y equals mx plus b. Okay, that is a line. Okay, we're going to go ahead and connect the dots that we have. Okay, remember, we cannot cross the green vertical line, so we have to stay on the left side here. Okay, but when you look at your condition, remember this rule holds as long as your x values are less than -2. Okay, so it's not just going to stop here at -5 because that was our last point. It's going to keep going this direction. Okay, because it has to exist for all x values less than -2. Okay, so we need to put an arrow on here. If you don't, that means your graph stops and it's going to change your domain. Okay, this is rule 1. All right, so now I'm going to make a table of values for rule 2. Okay, so I'm going to come over here. For rule 2, again, we're going to make a table, so we get to pick the x values, and this time the formula is -2x minus 3 that we will plug into to get the y values. Okay, so let's do this. All right, so we're going to get the y values here are going to be -2x minus 3. Okay, all right, we are switching over to rule 2. Okay, so we're looking at this condition. Okay, the x values for this particular piece have to be greater than or equal to -2. The very first thing you want to throw in your table is where the rule changes. That's happening at x equals -2. Has to be in your table. Then you want to pick things that are bigger than -2. Okay, so that's -1, 0, 1, and so on. Okay, so we're going to plug each of these guys into our formula. Okay, again, if you look at this formula, it's y equals mx plus b. It's going to be another line. Okay, all right, so the y value of x is -2. Okay, go to your formula. Everywhere you see x, plug in -2. We're going to get -2 times -2 minus 3. Okay, that's going to be 4 minus 3, which is 1. Okay, so that means if x is -2, y is 1. Okay, and then we'll move on to x equals -1. And so we'll get y is -2 times -1 minus 3. Okay, so we'll get -2 times -1 is 2. Okay, minus 3 is -1. So if x is -1, the y value is also going to be -1. And then we'll plug in x equals 0. Okay, so that means y is going to be -2 times 0 minus 3. That is 0 minus 3, which is -3. So that's corresponding to the point 0, -3. And then lastly, we'll plug in y equals 1. Okay, so we'll get -2 times 1 minus 3. That's -2 minus 3. That's -5. Okay, so your last point to plot here will be 1, -5. Okay, before we can plot these guys out, okay, we have to check where the rule changes. Okay, so that's the first point based on how we do this. Okay, so for rule 2, was it legal to plug in x equals -2? We'll look at your if condition. Okay, if x is greater than or equal to -2, yes, you can plug in -2 because of the greater than or equal to. Okay, so -2, 1 is going to be a valid point. Okay, so this is going to be a closed circle. Okay, so here we go. Okay, let's plot these guys out. Okay, we're going to start at -2, 1. That's going to be a closed circle. Well, what do you know? When you go to -2, 1, you can see it's an open circle from rule 1. Okay, so what happens? Okay, rule 1 says it's an open circle. Rule 2 says it's a closed circle. Okay, well, it's not part of rule 1, but it is part of rule 2, so we're going to go ahead and close it. Okay, so we're going to shade it in because of rule 2. Okay, and then remember, everything else will be closed for rule 2. So we're going to plot -1, -1, and then 0, -3, and then 1, -5. Okay, so you can see the line forming. Okay, so we're going to go ahead and connect the dots. Okay, we're going to start here. Okay, remember we can't cross the green vertical line, so this will just exist to the right of the green vertical line. Okay, and according to the rule, this rule 2 exists for all x values greater than or equal to -2. Okay, so we don't stop here, we keep going. Okay, because you have to have an output if the x value is 6, for example. Okay, so we're going to put the arrowhead like this. Okay, this is the complete graph. Okay, this is different here. Okay, if you go back to example 1, we had 2 pieces that were not connected. Okay, but this time we have 2 pieces that are connected. Okay, it just depends upon your function whether your pieces will be connected or if they're not connected. Okay. All right, so we're moving on to part B now. Okay, in part B, that's where we have to evaluate the function. So we're going to plug in an x value and write down the corresponding y value. Again, because this is a function, okay, not only do you have to pass the vertical line test in terms of the graph, but when you do the evaluation here, every time you plug something in, there can only be one output. Okay, you do not go and plug your x value into both rules. Okay, so let's start. The first one we're going to find is g of -5. Okay, and remember when we talked about this in example 1, you can either do this from the graph or from the formula. Okay, when you see g of -5, whatever's in parentheses, that's your x value. Okay, so here x is going to be -5. Okay, so basically you need to go and look. Here's where x equals -5. You need to find the point on the graph. Okay, this is going to be -5, -2. Okay, so this tells us that if x is -5, the y value is -2. Okay, so the answer is -2. Okay, one input gives you one output. Okay, again, you could have done this from the formula. Okay, if x is -5, that fits the bill of rule number 1 because -5 is less than -2. Okay, so here I'll write that down. For this one, you could use rule 1, okay, which is x plus 3. You would just do -5 plus 3 to get the -2. Okay, moving on to g of -2. Okay, so in this case, the x value is -2. Okay, so again, we're going to go to the graph. We're going to find where x equals -2. That's right here. Okay, go to the graph. Okay, it is the point on the graph that corresponds to x equals -2 is the closed circle. It's -2, 1. Okay, that is the open circle that we filled in. Okay, so it is a closed circle. Okay, so that tells us that if x is -2, the y value is 1. Okay, so that's the answer there. Again, we could have used a rule. Okay, if you go up here, you pick the rule that works for x equals -2. That's the second rule because you can actually, x can actually equal -2 there. Okay, so if we used that rule, okay, we could use rule 2 on this one. Okay, so the rule here is -2 x minus 3. That would give us -2 times -2 minus 3. That's 4 minus 3, which is 1. Okay, so it's up to you whether you like the graph method or the formula method. Okay, moving on to g of -1. Okay, in this case, your x value is -1. Okay, go to your graph. Here is where x equals -1. We want to find the corresponding point on the graph. That's this blue dot right here. If you look at my cursor, this is -1, -1. Okay, so if x is -1, the output is going to be -1. Okay, again, looking at the formula, if your x value is -1, that's going to cause you to use rule number 2 because x value of -1 is bigger than -2. Okay, so here you would use rule 2. Okay, so I'll write that down for you. So for rule 2, negative 2x minus 3, you would plug in negative 1 for x. You'd get negative 2 times negative 1 minus 3. Negative 2 times negative 1 is positive 2 minus 3, which gives you the negative 1. Okay. Lastly, if you're looking at g of 7, okay, in this case, your x value is 7. Okay. So when you go to the graph, here's where x equals 7. And notice the y value is going to be way down here. It's off the grid. Okay. Don't make the mistake and say undefined or there isn't one. It's off the graph. We can't read it. Okay. So to get this, you absolutely have to use the formula. Okay. So if x is 7, that's going to cause you to use rule 2 because 7 is bigger than negative 2. Okay. So we need to use rule 2 here. Okay, so we've got negative 2x minus 3. We're going to plug in x equals 7. So it's going to be negative 2 times 7 minus 3. That's going to be negative 14 minus 3. The answer here is negative 17. Okay, that makes sense. Okay, because we expected a pretty negative y value. Okay, based on the graph. Okay, so that's how you can do this. Okay, so we're done with part B. All right, so now we're going to that great question of domain and range. Okay, so again, this one is probably very easy because the pieces are connected. Okay, so it's like finding the domain and range of a normal graph. Okay, you can look at this. Okay, if you're doing domain, you want to write down your x values. You want to go from your leftmost point to your rightmost point. If you're looking at the leftmost point, remember this piece keeps going down, 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 down forever. So the leftmost point is essentially negative infinity. This piece is going down, 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 down forever. Okay, so it is covering the positive x values here. Okay, so the domain here is going to be all real numbers. Okay, you can also do the little number line trick I taught you if you're ever in doubt. Okay, I'll come up here and do it. To do the domain here, you're going to draw a number line to represent your x values. Okay, so what you would do here, you're first going to put where the rule changes. It changes at x equals negative 2. Okay, the condition on rule 1. Okay, the condition on rule 1, it covers x values that are strictly less than negative 2. Okay, so we have to exclude negative 2, but rule 1 covers everything less than it. And then rule 2 comes in. X can actually equal negative 2 there, so we fill it in. And then this rule covers all x values bigger than negative 2. Okay, so you can see the domain is going to be all real numbers. Okay, the range, again, it shouldn't be too much of an issue here because the graph is connected, the pieces are connected. So you're going to write down your y values. You're going to go from your low point to your high point. Okay, because both pieces are going down, 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 down forever, the lowest y value is going to be negative infinity. Okay, we're going to find our high point. The highest point on the graph right here is that closed circle at negative 2, 1. So you're going to write down the y value, which is 1. And since that is a closed circle, you're going to want to include it. Okay. If you did the number line thing here, okay, it may not make as much sense as, just writing down the range from the picture. But if you did that here, you could do it. You would make a number line and you would track the y values instead of the x values. Okay, so you would look at that first piece, the red piece. Okay, the red piece covers y values. The high point here is 1 and the red circle was open. Okay, so the red piece would cover y values less than 1. And then as far as the blue piece, it comes in and shades in this point negative 2, 1. So 1 would be included in the range, and then so that y value is covered, and then it goes down, 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 down forever. So the blue piece would cover y values of 1. It would shade it in, and then also everything less than it. Okay, so you can see the y values have to be 1 or smaller here for the graph. Okay, so it's your choice whether you like reading it off the graph or making these number lines. Okay, that's your domain and that is your range. And like I said, should be easier if you have a piecewise defined function where the pieces are connected. Okay, last part here, is the function g continuous on its domain? Remember what continuous means. Can you draw this graph without picking up your pencil? Okay, let's look at the finished product. Okay, go from left to right. If I'm on the red piece, okay, I travel, I get to -2, 1. It is a closed circle. Okay, so I just now start traveling along the blue piece. I don't have to pick up my pencil. The pieces are connected. Okay, so that means this particular function is continuous, because if you look at the finished product and you go from left to right on the graph, you can draw it without picking up your pencil.